Lesson 5, Equilibrium Ice Charts. The ice chart is used to find concentrations at equilibrium when given values prior to the system reaching equilibrium. Ice chart. I stands for initial concentrations. C is the expected change in concentration using X, 2X, 3X. And E are our concentrations at equilibrium. These are the steps we will follow. First, write the equation and make an ice chart. Then we write the Keq expression. Then substitute our determined concentrations at equilibrium into the Keq expression. We then solve for X. Then substitute X into your equilibrium values to find the equilibrium concentrations. And the last thing we do is check by substituting the equilibrium values back into the Keq expression and comparing it to the given Keq value. Now on a test, when you do this check, step 6, if it doesn't work out, I encourage you to move on to the next question. If time remains, you can go back and fix that question. But don't get hung up trying to get a question to work when it might be some small error that is hanging you up and you don't get to any of the other questions and I can't give you any marks for anything else on the test. So if time permits, go back, do your checks, and if the check didn't work out, then redo the question, see if you can find out where you made that error. Example 1, determine equilibrium concentrations if the initial concentrations are 0.1 molar Hi, 0.030 molar I2, and there is no H2 initially present. So step 1 said, I write my balanced equation and make an ice chart. So I'm starting off with 0.1 molar Hi, 0.030 molar I2, and there is no H2. I know that 0 can't go down, so the H2 is going to have to go up. So it's going to increase by X amount. And if the H2 is going up, I2 is also on the same side as H2, so I2 will also have to increase. And if the formulas on the right-hand side are going up, that means the formulas on the left-hand side are going to have to go down. Now this is where I write negative 2x, because when an H2 is formed, an I2 is also formed. And when an H2 is formed, two HIs are used up. So the numbers used in front of the x's come from the balanced equation. So at equilibrium, HI is going to be 0.1 subtract 2x. At equilibrium, I2 will be 0.030 plus x. And again, at equilibrium, H2 will just equal x. Now, I write my Keq expression. So Keq equals products over reactants. The way the reaction has been written, I2 and H2 are my products, so they go on top. And I put that over my reactants. And in the equation, my reactants are 2 HIs. So that is over HI squared. So we've made our ice chart. We have our Keq expression. I will now substitute in my equilibrium values. So the Keq in the question is 1.84 times 10 to the negative 2. If we look at our ice chart at equilibrium, HI is equal to 0.1 subtract 2x, so that got substituted into the denominator. I2 is 0.030 plus x, so that got substituted in for I2. And H2 is equal to just x, so I substituted that in for x. My first step will be to distribute the x into the numerator. And that will give me x squared plus 0.030x. Now I'm going to want to FOIL the denominator. And when I FOIL the denominator, I get 4x squared subtract 0.4x plus 0.01. My next step will be to multiply both sides by the denominator on the right-hand side. So I'll multiply both sides by 4x squared subtract 0.4x plus 0.01. And that will give me this. Now I'm going to distribute 1.84 times 10 to the negative 2 into the brackets. And I now have this. Now I want to put all my x squared terms on the same side, x terms on the same side, and my non-x terms on the same side. I want to move everything over to one side. Now what side to choose? Personal preference, I like to always make the x squared term positive. So that means I'm going to be moving everything over to the right-hand side. So I'll start by subtracting 0.0736x squared from both sides. So 1x squared subtract 0.0736x squared gives me 0.9264x squared. Now I'll move the x term by adding 0.00736x to both sides. So 0.030x plus 0.00736x gives me 0.03736x. And now I will subtract 0.000184 from both sides. And that's all equal to 0. Now I've got an x squared term, x term, and non-x term. The x squared term is my a value. The x term is my b value. And the non-x term is my c value. And that will all go into my quadratic equation. After I've written the numbers into the quadratic equation, I want to add 3 sets of brackets. The first thing I want to do is bracket the entire denominator. Then I want to make sure that I bracket the entire numerator. And then I want to bracket everything that is underneath the square root sign. When I punch that into my calculator, if I've done it correctly, I will get 0.004436905. Now to finish the question off, we said that x equals 0.0044366905. So I'm going to substitute x into the equilibrium concentrations to find out what the concentrations of the products and the reactants are when the system is in equilibrium. So the HI concentration is equal to 0.1 subtract 2x, which gives me 0.091 molar. The I2 concentration is equal to 0.030 plus x, which gives me 0.034 molar. And the H2 concentration equals x, which is 0.0044 molar. Now, where did my significant figures come from? Well, going through the quadratic to solve for x, this is the shortcut we're going to take. We're just going to say if we have 3 significant figures in the HI, we've got 2 significant figures in the I2, and our KQ has 3 significant figures, then our answer will be limited to 2 significant figures. The lowest number of significant figures in the numbers that we have been given. When we substitute in, we are doing addition and subtraction. So if I look at HI, 0.100 is good to 3 decimal places. My x value is good to 4 decimal places. So that means my answer is only good to 3 decimal places. The I2, also 0.030 is good to 3 decimal places. X value to 4 decimal places, so my answer is only good to 3 decimal places. And the H2 is equal to x, and x had 2 significant figures, so that means H2 had 2 significant figures. Now, to check, I will take these numbers pre-rounded and stick them back into the Keq expression. And when I run it through my calculator, I get 1.84 times 10 to the negative 2, which is my original Keq value, which means I've done everything correctly. Shortcut number 1. If the Keq value strongly favors what we are starting with, that's the products or the reactants, then the initial concentrations will be similar to the final concentration. The change will be nominal. Remember, we consider an exponent greater than 3 as strongly favoring. This will allow us to simplify our ice chart and avoid using the quadratic equation. So we have a Keq value that strongly favors a reactants. When I look at the equation and separate my reactants from products, I see that I'm starting with just reactants. So in the event that my Keq strongly favors reactants and my initial line has me starting with just reactants, I can get rid of the x's on the reactant side. All right, so this symbolizes our reactants and products. And before we start, it's all reactants and no products.
And when we're in equilibrium, we see from the equilibrium constant that it strongly favors reactants. So when in equilibrium, it looks more like this. Boop, there we go. So I have almost all reactants and very few products. Now, why can I get rid of the X on the reactant side? Well, because this amount hasn't really changed much. Whatever I had at the beginning, subtract the amount that got moved over to products, is essentially the same number, significant figure-wise. Products, I can't get rid of the X because anything added to 0 is a significant change. So the X's stay on the product side, but we can get rid of the X's on the reactant side.
So RRR favors reactants. Starting with reactants, get rid of the X's on the reactant side. Now this time my Keq value strongly favors the products. When I look at my reaction and separate reactants from products, I see in my initial line I'm starting with just products. So when my Keq strongly favors products, and I'm starting with just products, I can eliminate the X on the product side.
So this time we're starting with products and we don't have any reactants. If we look at the Keq, it strongly favors products. So that means when we are in equilibrium, it's going to look more like this. Whoop, there's going to be some reactants in there. But since it strongly favors products, almost everything's going to be products. There are going to be very few reactants. So the amount that we started with product-wise, subtract the amount that went over to reactants, significant figure-wise, that gives us what we initially had anyway. So that's why we can eliminate the X's on the product side, is because the amount of products hasn't really changed. We got to keep the X's on the reactant side because anything added to 0 is a significant addition, so those X's on the reactant side have to stay.
PPP strongly favors products. Starting with just products, eliminate the X on the product side. This time our Keq slightly favors the reactants. If we look at our products and reactants, we are starting with just reactants.
So here we have our initial concentrations. We're starting with all reactants, we don't have any products. We look at the Keq value, it says that reactants are slightly favored. So this is our starting point, but when we're in equilibrium, it's going to look something like this. Reactants are slightly favored. Now the reason we can't drop the X is because the amount that came out of reactants did make a significant difference to the amount of reactants that we have when the system's in equilibrium. So in this case, we can't eliminate the X. When the X is subtracted from the initial amount, significant figure-wise, it will make a difference.
If the reaction does not strongly favor any side, or we are not starting with the side that is strongly favored, we cannot eliminate anything from the equation, which means odds are we're going to be going to the quadratic equation. Determine equilibrium concentrations, knowing that the initial concentration of I2 is 0.200 molar, and there is no I initially present. So I write my ice chart, and I'm told the I2 concentration is 0.2, and the I concentration is 0. That means that the right-hand side is going to have to go up because 0 can't go down. It's going to go up 2x amount. The 2 comes from the balanced equation. There are 2 I's in the balanced equation. And if the right side goes up, that means the left side has to go down. So it's going down 1x. And that is because in the balanced equation, there is 1 I2. The coefficients used to balance the equation are the coefficients that will be used in the C line, the change line. So at equilibrium, I2 concentration will be 0.2, subtract x, and the I concentration will be 2x. Note the Keq strongly favors the reactants. When we look at the ice chart, our initial line tells us that we are starting with just reactants. And we had said when the Keq strongly favors the reactants, and we are starting with just reactants, we can eliminate the X on the reactant side. Now I write the Keq expression and I sub my numbers in. the first thing I will do is square the 2x. So 2x multiplied by 2x equals 4x squared. Now I will multiply both sides by 0.2. That will give me 0.2 multiplied by 3.80 times 10 to the negative 5 equals 4x squared. Now I'm going to multiply 0.2 by 3.8 times 10 to the negative 5. And that gives me 7.60 times 10 to the negative 6 is equal to 4x squared. To get x by itself, I will divide both sides by 4. And then I will take the square root of both sides. And I get an x value of 1.3784 times 10 to the negative 3. Now that I've found x, I'm going to substitute x in to find the concentrations at equilibrium. I2 is equal to 0.2 subtract x, but didn't we eliminate that x? Note that the x is added back in when calculating the equilibrium concentrations. So 0.200 subtract our x value gives us 0.199 molar. So it did make a difference, but not much of a difference. I should also point out that when we drop the x, it is actually making an approximation of what the concentrations will be at equilibrium. It won't be as accurate as the numbers that we would get if we went through the quadratic equation. Inside the answer key, there will usually be two sets of answers. One for if you drop the x, one for if you went through and used the quadratic equation. Now the I concentration is equal to 2 multiplied by x, and that gives us 0.00276 molar. To see if I did everything correctly, I will then sub those numbers into the Keq expression, and I wind up getting 3.80 times 10 to the negative 5, which is my Keq value, so I know I've done everything correctly. Shortcut number 2. Example 3. Initial concentrations of 0.2 molar I2, 0.2 molar H2, and no HI. I start by making my ice chart. Like we said, I2 is 0.2, H2 is 0.2, and the HI, there is none. So that means the right-hand side is going to have to go up because, well, 0 only has one way to go, and that's to increase. So the change for HI is going to be plus 2x. 2x because there's a 2 used to balance the equation. And when two HIs are made, one I2 is used up and one H2 is used up. So I2 is going to go down X amount, H2 is going to go down X amount. At equilibrium, I will then be, the iodine will be 0.2 subtract X, hydrogen will be 0.2 subtract X, and the hydroiodic acid will be 2X. Now we write our Keq expression, that's products over reactants. Now we'll substitute the numbers that we have for equilibrium into the equilibrium expression. So Keq is 64, our HI is 2x, and that's 2x squared, and on the bottom we have 0.2 subtract x multiplied by 0.2 subtract x. Now I can also write this as 0.2 subtract x squared on the bottom. If we got a nice squared number on the top and the bottom, that means we can make a shortcut here, which is taking the square root of both sides. So when I do that, this is what I'll get. Now to solve for x, I'm going to multiply both sides by the denominator on the right-hand side. And that gives me 8 multiplied by 0.2 subtract x in brackets equals 2x. I'll distribute the 8 into the brackets. Now I'll move my x terms to one side, my non-x terms to the other. So I will add 8x to both sides. And to get x by itself, I will divide both sides by 10. So I end up with x is equal to 0.160. I will now substitute that in for my concentrations at equilibrium. So I2 equals H2, and they both equal 0.2 subtract X, so that gives me 0.040 molar. Now, question is, why only two significant figures there? Well, it's because of the subtraction when I substituted the X in. 0.200 is good to 3 decimal places. My X value is 0.160, which is good to 3 decimal places. So when I subtract, my answer is only good to 3 decimal places. And that's how I wound up with two significant figures. HI is equal to 2 multiplied by X. So 2 multiplied by 0.160 gives me a concentration of 0.320 molar. Now, if given time on the exam, I would check this by substituting the values I found back into the equation. So HI squared divided by 0.04 divided by 0.04 gives me 64.0. And it looks like I've done everything correctly. Example 4. A system is in equilibrium with the initial concentrations of 0.025 molar I2, 0.025 molar H2, and 0.400 molar HI. What will be the new equilibrium concentrations if enough H2 is added to initially increase its concentration by 0.050 molar? How does this question differ from the previous question? Well, if you said we weren't given a KQ, that's correct. So question is, how are we going to find the KQ value? Well, we're told the system is in equilibrium when the initial concentrations of I2 and H2 are both 0.025 molar and that the HI concentration is 0.400 molar. So the system is in equilibrium. So if we sub those values into the KQ expression, we can find the KQ value. So we take out the KQ expression, we substitute those numbers in, and we wind up with a KEQ for this reaction of 256. So now let's write the equation and make the ice chart. Question 1 though, when we look at this ice chart is, how did we get that initial line? I2 is 0.025, but now it says H2 is 0.075. Now the question says enough H2 was added to increase it by 0.050 molar. So we started with 0.025, we increased it by 0.050, which means we wound up with a concentration of H2 of 0.075. That makes sense. So that's our new total. How do I know what way to shift? Because it says the positives are on the right, the negatives are on the left. Where did that come from? Well, that's EQ1 assignment. That's Le Chatelier's principle. Because if I increased H2, the system wants to decrease H2. So the system shifts away from the H2. Right, so the stuff on the right goes up, the stuff on the left goes down. So we're going to start by substituting in the KEQ values. We found KQ to equal 256, and we substitute in 0.4 plus 2x for HI, 0.025 subtract x for I2, and 0.075 subtract x for H2. I'm going to write the numerator out in a longer form so it's easier for me to FOIL those numbers, because I'm going to have to FOIL the top and I'm going to have to FOIL the bottom. Now I'm going to multiply both sides by the denominator. When I do that, I wind up with 256 multiplied by everything that was in the denominator, and that's equal to 4x squared plus 1.6x plus 0.016. Now I'm going to distribute 256 into the brackets. And when I do that, I wind up with 256x squared subtract 25.6x plus 0.48. Now I want to move everything either to the left-hand side or right-hand side. And as I mentioned in class, I like to keep my x squared value positive. So that means this time I'm going to move everything to the left-hand side. Although, truth be told, it really doesn't matter which side you move it to. So I'm going to subtract 4x squared from both sides To move 1.6x, I'm going to subtract 1.6x from both sides. And to move the 0.16, I'm going to subtract 0.16 from both sides. So 256x squared becomes 252x squared. Negative 25.6 subtract 1.6 gives me negative 27.2x. And 0.48 subtract 0.16 gives me 0.32. That is my A. So my A value is 252. My B value is negative 27.2. And my C value is 0.32. So I put that into the quadratic equation. Remember, write out the quadratic first, then add your 3 sets of brackets. The brackets that will encompass the entire denominator, the entire numerator, and the other set of brackets that will encompass everything that's supposed to be underneath the square root sign. I punch that into my calculator. I wind up with x is equal to 0.01343763. Now that I have an x value, I go back to my equilibrium values and I sub that x value in. So I2 equals 0.025, subtract that x value, and that gives me 0.012 molar. H2 is 0.075, subtract x, which then gives me 0.062 molar. And HI is 0.4 plus 2 times the x value, which gives me then 0.427. Last thing I want to do, if I have time, is substitute those numbers back into the Keq expression. And I see that I wind up with 256, which was my initial Keq value, so everything is good. Now note, when I actually did the check, I put the pre-rounded numbers into the equation, and that's how I wound up with 256. If I'm using rounded numbers, I may not wind up with the exact same number I started with. Very close, but not the exact same number that I started with. That's the end of the lesson. You're good to work on the EQ3 assignment.